During class last week, we covered the derivation of the rotation matrix, okay, two-dimensional rotation matrix. And we came up to the conclusion that basically the rotation matrix, okay, during our derivation, we were trying to, represent a point uh, in a different frame. So the point is given in frame one, and we were trying to represent it in frame zero. So we came up with this matrix here, okay, that we denoted by R1 to 0, okay, R1 to 0, that takes a vector in frame one and transforms its representation to frame 0. And then basically this is the objective of the rotation matrix, okay? Transforms back the vector from its representation in frame one, okay, and gets it back to frame 0, all right? And we said that, this is an important information to remember, we said that the columns of the rotation matrix are 1 to 0 are basically the projections of frame 1 coordinates on to frame 0 frame. Okay, so this is x sub 1 in 0, okay, in which we take the dot product with x0 and y0 in 0, of course. Okay, so we here we decompose x1 in 0 to its components, the two components of x0 and y0, the two coordinate frames of the two coordinates of frame 0. So this is basically if you have a frame in which it is rotated from another frame, and all what you need to do to derive the rotation matrix is to try to let me go back to the figure so that you so you try to find the representation of x1 as a unit vector, okay? It's a projection, or it's vector projections into x0 and y0. This is the first column of your rotation matrix, and also find the projection, the vector projection of y1 into x0 and y0. Remember that x0 is extended here, so you have a negative x0 component here and positive y0 component. Depending on theta, of course, it might be positive, it might be negative. So it depends on the quadrant that you end up with. So in the next video, we are going to take an example and see how we can derive the rotation matrix of this example.